Welcome back 1200. We are doing interference and diffraction patterns this week. Actually, we're going to be doing it for 2 weeks. This is another two-part lab. Now, when we started geometric optics, I had strongly suggested that you read your textbook prior to doing the lab. And I'm going to do the same. I'm going to say the same thing. I'm going to make the same suggestion for this lab, although it is for different reasons. Now, for the geometric optics lab, it just served the purpose of utilizing your time in the best way possible. You are going to reinforce what you've already learned by doing the lab. Okay, yeah, and there's a lot of things to grasp and remember while we did the lab. But anyway, with this particular one, if you've never seen this material before and you just go by the lab manual, you may get very discouraged. If I've never seen this before and I was going off that lab manual, I'd probably throw it and like give up at some point. And the reason being is that, well, although the equations that you're going to be using to analyze this data are very straightforward, to derive them and explain them, you need to be quite wordy, and you need a lot of graphs or pictures and diagrams. So when the author presents this material to you in the lab manual, it's very condensed. So it's a challenge. So don't get discouraged. Remember what I said. If things aren't looking good, just study this on your own in your textbook and then start analyzing the data. With that said, I will go over the equipment we're going to be using for the next 2 weeks. So we have a Cornell plate. By the way, there's a diagram of this in your lab manual, and all it is some double slits. Double slits in different configurations, like the distance basically between those two vertical slits. There's also single slits with different widths to them. And let's see what else. Oh, there are multiple slits, just a variety of slits. And we're going to be using that today. We are also going to be using this laser here. That is a, a helium neon laser. Its wavelength is 632.8 nanometers. All this will be in your data sheet, however, so you don't have to retain any of this. But that's basically it. We mount the laser to our optic track, shine it through the Cornell plate, and way over there we are going to cast an image, and that image will be that interference or diffraction pattern. Let's see. What I will do is, for the heck of it, put you on pause and you'll take a look at what you would normally see in a darkened lab. So hold on. So what you're looking at right now is the other side of my garage with that white piece of paper there that we'll use as a screen. I will turn on the laser. Usually it takes a few seconds for it to turn on. Okay, there we go. So there are the fringes. Let me turn off the lights here. Let me zoom in on that for you. Now, I got to warn you that, or just mention, that the camera doesn't do it justice. If you're looking at this in person, the fringes are more well defined. Those fringes have so much intensity that the camera on the phone kind of blends some of the fringes together. But nevertheless, there is our pattern. So what I will do is photograph the different patterns from different number of slits or slit distances or single slit with distant widths and so forth. Whatever your lab manual asks you to do, I will go ahead and supply you with the photograph. Now, let me put you on pause for a second, and I want to say a few words about the photographs. Actually, I don't need to put you on pause. So I just turned the lights back on, and yes, you really can't see the fringes, but what I want to say is that in your data sheet, what you're going to be, well, let me dim the lights a little bit. In your data sheet, what you'll see is a ruler, something like this. So I will tape that to the screen and you will be able to use that ruler to measure the distances in question. So that is a centimeter scale. And I did, however, photograph these fringes in different lighting than we have now. I adjusted the light so that the image is captured as best possible for you to take accurate measurements. Oh, by the way, well, let me put you on pause. So for this Cornell plate, you are going to be analyzing 8 sets of data. You have double slits, 2 different configurations. You have multiple slits. I gave you a 3 and a 4. Then you have single slit diffraction patterns, and I gave you photographs of 4 different single slits. Each slit has a different width. So that is your data. I want to let you know that what I did was I analyzed the data myself based on the photographs, and that was just my way of ensuring that the data I present to you is that you're more than capable of getting meaningful results. So you're going to make comparisons. For instance, for the first part, you're going to determine the wavelength of our source, which is known, and in another part, you're going to compare. You're going to find an angle. Now, for some of these, I got, well, for one, 0% error. For, I think the most I got was maybe like just 2% error. So it all hinges on how careful you are making these measurements, basically, if you take your time or not. Yeah, well, and of course, if you're using the correct formula. But it's all good. Now, let me put you on pause so I can show you the Newton's rings equipment. Okay, here's our equipment for Newton's rings. Now, typically this is the most challenging part of the lab for students to do. Luckily, it's going to be the easiest for you. And the reason being is that the analysis is very straightforward. But viewing this can be difficult. And the reason being is that this needs to be set up in a very particular way, and it's very sensitive. So I mean, I could set this up so that you see the rings clearly, and all it takes is someone to like bump the desk or any of this, and throws it out of whack. So someone could spend a lot of time trying to get those rings back in view, but then they just abandoned it. But anyway, you're not going to have that problem, obviously. The other thing with this is reading a traveling microscope. So you could spin this wheel, and there's a stationary, what do you call it, scale here, and a scale on this wheel. I can read a distance with an absolute error of 10,000ths of a centimeter. So if you're seeing this for the first time, plus this lab is usually done in the dark, it can be difficult to read. I was thinking of photographing the scale after I move it to a new ring and providing you that photograph in the data sheet, so you would have to determine on your own what the measurement is. And the reason being is just to gain some practice with using something like this. But you know what? You really need hands-on practice to get a sense of how this works, so forget about that. What I'll do is I'll just provide you with the measurement. How this works, or what the setup is. By the way, there is a diagram of this in your lab manual, and to view these rings, what you need is like a flat slab of glass, and sitting on that is another piece of glass that is spherical. Well, the top part is flat or horizontal, but the bottom part is spherical. So you have those two pieces just sitting on top of each other. And we have those two glasses indeed in this container here. And this is just so that, you know, they don't get scratched. You don't lose one of them. But that's what this is. So we slide this underneath the traveling microscope. You probably can't see this piece of glass. It's at a 45-degree angle. It's mounted to this bracket here. I can position it wherever. And that's just a clear piece of glass. the light comes in, strikes that glass. Some of the light is reflected downwards. It goes through the two pieces of glass stacked on top of each other, and then some of the light is reflected back upwards into the microscope where I'm looking and I can see the rings. Now, to view these rings, we need a monochromatic and coherent light source. Also, with a particular wavelength, or there's a target wavelength. I mean, it would work with any wavelength, but for the size of the pieces of glass in here, we want those rings to be a certain distance from each other. We want to be able to view it in a practical way and be able to take measurements. So we want there's a certain range of wavelengths that work best, and what better than to use a sodium bulb source. So the wavelength will be given to you in your data sheet, and what I'll do is get the camera, place it above the microscope, and take photos. By the way, inside this microscope there's like crosshairs, so that's where you'll know where I'm measuring from. And that is it for Newton's rings. So let me put you on pause and finish this off. But before we do that, you know what? Let me just grab the camera and put it over the eyepiece just to give you a peek of what you'll be seeing. Why not, right? So hold on. So there you go. It's kind of difficult to hold this phone steady, but there are your Newton's rings. All right, let me put you on pause and we'll get back to the rest of the lab. So for geometric optics, there was a lot to do, right? A lot of different configurations. For those 2 weeks, it took us I want to say 2 hours and 45 minutes of video. For this one here, there's stuff for us to do, but we're dealing with a minimal amount of equipment. Come on, we're just shining a laser through that plate. It's just through different configurations of slits. So that's it. We're done. All you need to do now is take a look at that data sheet and do the analysis. But this was a short video for you guys, and I will see you next week.